Good day, everyone. Welcome to our lecture on algorithm analysis. Just as problem is analyzed before writing the algorithm, when we want to solve a problem, so we have to analyze the problem and write an algorithm, and then create a program. Now, after we create an algorithm which is designed to solve for that problem, it's not only that we analyze the problem, but we must also analyze an algorithm. Usually, there are different ways on how to design a particular algorithm and how to analyze or measure the efficiency of the algorithm, which will be presented in the next slides. There are certain algorithms which take little computer time when executing, little computer time of execution. However, there are also others which takes a considerable amount of time. Again, it depends on how we design an algorithm. In this lecture, we will have 7 different topics. The first one will be introduction. We'll be discussing some terms. Then we'll go to defining an experimental study and some higher level analysis. Then we will be discussing about growth rate of functions and a note from an author of our reference that we have to focus on the worst case scenario of an algorithm. Then after we will be discussing the different notations in the asymptotic analysis. Lesson 6 or section 6 will be discussing big O notation, and the last slides or the last section will be discussing the other notations, which are the big omega and the big theta. Let's start first with some terms that we need to know when analyzing algorithm. So in analyzing algorithm, we count the operations, no, in order to assess its efficiency. These lecture notes, this section, the notes or the discussion for this section is taken from the book of Carrano, which is Data Abstraction and Problem Solving with C++, Walls and Mirrors, 5th edition. Algorithm can be analyzed by 2 factors. The first one is the space, and the second one is using or through time. So we call them space and time complexities. When we say time complexity, it is um, it is the amount of time taken by an algorithm to run the program completely. It is sometimes it is also called the running time of the program. So when analyzing algorithm, one is dealing with the time complexity of that algorithm. The time complexity of the algorithm depends on the input size. When we say input size, um, that means the values within, for example, if you have a loop, no, when you have a loop that counts from 1 to 10, then the input size is 10. Okay. However, if we don't know the size of that loop or the number of iterations, and it would depend on the value inputted or entered by a user, then we will denote n. Okay, so that will be our input size. Now, the complexity is the time complexity is commonly represented by the big O notation, which will we be discussing in the next sections or in the next slides. Then the other one is the space complexity. So the space complexity of an algorithm is the amount of memory space required to run a program completely. So the space complexity of an algorithm depends also in the input size. For this lecture, we will be dealing more on the time complexity, which is this highlighted, no, which was highlighted. So this will be, we will be discussing notations that measures time complexity depending on the input size, which later on, no, later on the slides, we'll have the different methods, or we say notations. Okay, now the time complexity has categories. The first one is the best case. Uh, Then we also have the average case, and we also have the worst case running time. In the best case, in running time, so the performance of an algorithm will be best under the optimal conditions. So say, for example, if you have a search algorithm, a linear search algorithm, so the best case will be when you search an array or a list, you will find it in the first element of that data structure. So that will be the best case. The average case will be if you find it in the middle or somewhere between the last and the first and the last element. So that's an average case. Well, the worst case is when you find the value at the last element of the array or nothing at all, which means you have performed several iterations before you have searched or before you get a result, no, of your search. Okay, so that's the difference among these three categories of time complexity. And that ends our first section. The second topic or the second section will be about experimental studies. Now, one way to study the efficiency of an algorithm is to implement the algorithm and experiment by running the program on various test inputs. And then we will record the time spent during each execution. So this is what is experimental studies is all about. Meaning we will be analyzing the algorithm based on experiments. Okay, we will be inputting different sizes of n. Then we will check the time of execution. Now, in Java, we will be using this method, the current time millis. This current time millis method will be returning a time value which is in milliseconds. So we will use this system, that current time millis, okay, to record the starting time, and we will also be declaring another long variable an end time, no, of a long type. We record it at the end time. In between these two current time millis is our algorithm. Whatever our code will be placed in between these two um, calling of methods. Now we will have an instance here, another instance here. Then to get the time that takes to process this algorithm, we will then subtract end time by start time, and that will be our elapsed time. Now, this system that current time millis function will return again in terms of milliseconds, and it's actually calculating the number of time based on from January 1, 1970. So that is called the benchmark time known as the epoch. Okay, we will uh, we will be basing it at the epoch. So from the epoch, the start time until the end time, so we will subtract, and that would be of the time that it would take for the algorithm to perform. I have an example code later to show you what's the output of system that current time millis or the current time millis function. Okay, now we have here a code on the next slide. So you have to get the elapsed time based on the value of n. In this code or in the next code, we will be inputting the value or entering the value of n. Okay, here is part of the code. So kindly copy this code. You have to import java.util.scanner since we will be getting an input from the user. Then the class name will be this one. You can create your own class name. So you already know how to do that. And then you have here. You will just have to take note of this part here. Okay, this part here. So you have here current time millis. So again, this will be our start time. Then another would be our end time. So we'll be subtracting these two so that we can get the elapsed time. So the elapsed time again is the time it would take for the algorithm to process, or the time uh, it take for the algorithm to finish processing. Now our algorithm is this function, or this method rather, repeat one. Now in repeat one, there are parameters. You have ch for character, no, character value, and num for n. Now that will be our n. So the number of, let's say, iterations, if this is loop. Then we will print it so that we'll be able to determine what is the value of the elapsed time. And also, there are actually two functions here, or two methods, which we will be comparing. Okay, the other one is called repeat two. The first one is repeat one. Oh, here they are. They're written in a different method. So you have, for repeat one, we will be getting a character C and an integer. No, that will be n. Then we'll just have to add them. Okay, we'll just have to concatenate the value of C, our character, until a value n. Now that will be inputted by us or by the user. So that's for the first method, which is the repeat one. Now wherein it will return the copies of and character using repeated concatenation. The other one, a different algorithm, will be using the string builder function or method to compose the n copies of that character. So here we'll be using this function or method that append. No, this function that append. Okay, string builder that append. So meaning we'll just have to append or add um, a character C. Okay, now I'll be just showing you first what it looks like now in the program. So okay, I am sharing you now the screen. So this is the equivalent code in Java. Now I am commenting first the other lines, the last lines, because I want you to see first what current time millis function looks like. Okay, we have here current time millis, start time, and end time. So let's run it. Now it's still building or compiling. So we'll just have to wait until it finish the compilation. Now, the time that it would take for the algorithm would depend on your processor. Now, that's a another or one big factor of the speed or the elapsed time, the value of the elapsed time. Okay, suppose we want to use the character asterisk, okay, and we'll have to process it since Uh, repeat one method is a loop. So meaning let's just say 100 times. No, loop it 100 times. So it will be displaying 100 stars. Okay. Then now take note of this again. The time here, okay, current time millis is actually calculating from the epoch. Okay, that will be a reference time, and that is January 1, 1970. Okay, I'll just have to check if the correct value of time of our epoch. Okay, okay, that's January 1, 1970. Okay, where's the output? Yeah. So here you have here a very big value. So that is why we use the long um, data structure or the long type, no, if element. Then the end time is this one. That's the start time again is 163,772,9405637 milliseconds. The end time is 163,772,9405777 milliseconds. And if we will subtract the two, we will get 114 milliseconds. So which means that in my computer, these 100 stars were being displayed, these stars were being displayed 100 times using the loop in repeat one within 140 milliseconds. Now, let's comment first the start time and the end time, and let's compare now the two algorithms. Now you take note that these two algorithms, repeat one and repeat two, performs the same function. Okay, that is displaying a character n times. Okay, an inputted or an entered character n times. Now let's compile it and run. Okay, now let's use another character. Let's say C, and we will be looping it, say, 200 times. Okay, now as you can see here, okay, for a while. Sorry about that. I've commented the wrong value. It's I I have not commented end time. I have commented elapsed time on the first one, so we'll just have to rerun it. Okay, C and 200 times. Okay, for my repeat one method, it took 75 milliseconds to process 200 characters, 200 Cs, no, displaying 200 Cs. While my repeat two method only took 2 milliseconds to display these 200 Cs. Now, as you can see, this second, this second function or method is much faster than the other one. So instead, therefore, if we want to use an algorithm, then we will have to use the second method, okay, which is the repeat two. So that is how we use, or that is how we perform experimental analysis now, when selecting an algorithm. Okay, now based on the book, so since the book has um, much faster speed. Okay, so these are the data. No, based on the book. Now I tried to run this 50,000 N, but um, the computer hung hung for a hung for a bit. So please do not try if you don't have a very powerful computer. I have a 2 point something gigahertz computer, and I think it's quite a dual core. No, it took a lot of time, no, for these 50,000 ends to be processed. So if however, if you really want to try it, then you can try it. But for for the authors, no, when they experimented the that algorithm, it only took 2,884 milliseconds for repeat one. However, as you can see here, no, if you take a look at the repeat two, okay, if you take a look at this repeat two method, no, the algorithm in repeat two only took 1 millisecond in performing 50,000 iterations. Now, in my computer earlier, so it took 150 milliseconds, if I'm not mistaken, 150 milliseconds for 200, 75 rather, sorry. That's 75 milliseconds for repeat one to display 200 characters, while 2 milliseconds for repeat two to display 200 characters. Here, they may have a more powerful computer, so it only took 2,884 milliseconds for n characters to be looped, while 1 millisecond for repeat 2. And as the number of n increases, no, they even tried 12 million, and this is a large value, the milliseconds, so that's 265,696,421 milliseconds. Okay, so this is here is 1 second. No, that's 6,000, meaning this is 6 seconds. So meaning if we want to convert this one, it's probably more than a day. So if you have 265,696 seconds, it's probably more than a day. It may be 3 days. Okay, 3 days for it to finish the 12,800,000 iterations. That is using the repeat one algorithm. Well, repeat two algorithm only took 135 milliseconds. So what have they done is that, of course, in my when I've shown you the operation, so I've shown you the two methods or the two algorithms performing. Now, but here they use a different program. The repeat one algorithm is run separately from repeat two algorithm. So repeat one, they run first repeat one, then record, then they run again repeat two, and then record the time. But take note, it should be run in the same computer. No? Do not compare algorithms using experimental studies in different computers. It's okay if for one computer you compare the algorithms, and you use another computer and perform or compare the same algorithms, but do not compare one algorithm performed in one computer and the other algorithm performed in the second computer, because it would not be a good basis, no, for comparison. Going back here, as you can see here, the repeat one algorithm, as the number of inputs increases, so it would take larger amount of time. Well, repeat two only took a very minimal amount of time. Okay, so again, that's one way of um, measuring the efficiency of algorithm through experimental studies, meaning you have to run the algorithm in a computer, in the same computer. You have to run when you compare algorithms, you have to run all of them within the same computer. However, there are challenges. One is already mentioned to you earlier. Okay, experimental running times of two algorithms are difficult directly to compare unless the experiments are performed in the same hardware and software environment. So as what I have told you, they should be performed within the same computer, within the same environment. The second one is experiments can be done only in a limited set of test inputs. If you observe the table in the previous slides, now, when they increase the number of ends, the number of input or the input size to millions, no, it took them number of days. No, so it took them more than 1 day to run or to complete the algorithm. So if you increase more, now something might happen or your computer might surrender. So there is only a limited set of test inputs if you use the experimental studies or experimental analysis. So hence they leave out running times of inputs not included in the experiment, and these inputs may be important. Yeah, probably when you increase the, you might find a very significant observation when you increase the number of or the input size to a much larger values. However, due to the limitations of our test environment or our computers, and there might be some difficulties or problems that would occur. Then, lastly, an algorithm must be fully implemented in order to execute it to study its running time experimentally. If you have observed earlier, I have presented a complete program for repeat 1 and repeat 2 algorithms. However, the book, my reference, had only actually presented the algorithms themselves, no, those two methods. So here, the challenge would be how would you implement to fully implement it, no, the algorithm. So you have to complete the program so that you can test the algorithm. So that's one challenge of using experimental analysis. So the algorithm must be fully implemented for it to be execute or in order to execute it to study its running time experimentally. Another is that when it's the algorithm is written in pseudocode, then you have to convert it into a programming language. Okay, so in order for you to fully implement that algorithm. So remember the challenges of experimental analysis. And now we are done with the second topic or second lesson. Okay, let's proceed to a different way of analyzing algorithms. So I call it higher level analysis. Now we will not be using experimental analysis, but a different type of analysis. Okay, let me just click this one. Okay, now to analyze an algorithm or the running time of an algorithm without performing the experiments, so we have to perform analysis directly based on um, the primitive operations, now directly based on the high level description of the algorithm. So it's either in the form of a pseudocode or its actual code. So we have to perform this on a higher level description of algorithm. That's why I have labeled the third topic as higher level analysis. So again, here here in this type of analysis, we can analyze the algorithm either based on its code or based on its pseudocode. So we define a set of primitive operations. So we will be dealing with the operations based on the algorithm presented. Okay, and these operations includes the value, assigning of value to a variable. That's one operation. Following an object reference is another operation. Performing operation, for example, adding two numbers might be composed of three operations. For example, if I have A is equal to X plus Y. Now, I have actually two operations here. The first one is the addition, and the second one is storing the value of the sum of X and Y to A. So that is how we count the operations. And also we have comparing two numbers. That's one operation. Uh, it might be more than one operations if the comparisons is more than two numbers were being compared or two values were being compared. Then accessing the element of an array by index. Okay, say for example, you directly access the array at index 1. So that's one operation. However, if you use in an iteration or a loop to access all the elements of the array, and that will be a different case. Now, for example, an array has n elements, then therefore the number of iterations or the number of operations will be based on n. Then we also have one operation for calling a method. And inside the method would be a different counts of operations, then another operation for performing or returning the value from a method. Okay. Formally, a primitive operation corresponds to low-level instruction with an execution time that is constant. Okay. Ideally, this might be the type of basic operation that is executed by the hardware, although many of our primitive operations may be translated to a small number of instructions. Now, some operations, just like here, this addition operations can be separated into this form and this one when you store the sum of these two to a. Okay. So how do we measure the operation of an algorithm? So we measure it using that operation or algorithm as a function of time. Now, to capture the growth, the order of the growth, okay, of an algorithm's running time, we will associate each algorithm a function that characterizes the number of primitive operations that are performed as a function of an input size n, meaning we will have to create an equation for the algorithm. A mathematical equation, now an algebraic equation, mathematical equation, of course, composed of variables to represent the running time of that algorithm. We call it the growth function of an algorithm. Let's have this example first. Now, suppose we have here a shop. Now, this one here is a shop. Okay. Okay. This one is a shop. I hope you can see the pointer. Okay, this one is a shop, and this shop accepts delivery, oh, door-to-door delivery, and we have, say for example, 50 packages to be distributed or to be delivered among 50 different houses. No, so the shop will have to make a route, okay, that so that all of the packages or the gifts from the shop will be delivered to the 50 houses. And based on the data, no idea based on the data, so since this is an example, let's just say that each of the house is 1 mile away from each other. Exactly 1 mile away from each other, which means also from this shop, the distance would be 1 mile. And from this house to another house, the distance is also 1 mile. To the other house, we have also 1 mile. So meaning in this problem, they have the same or equal distances among themselves. So what do you think would be the route? Now again, we as programmers will be performing or creating algorithms. No, um, we won't have. There would be times that we won't, or we would have different algorithms or different solutions to the problem. Now here we will be checking two different algorithms in distributing the packages among 50 houses. Okay, suppose there is one driver. Okay, one driver picks up all the 50 packages, and what he have done is that he drives 1 mile and distribute the package and drives another mile to the other one and so on. Now, how do we calculate the time or the number of miles that the driver have traveled from one house to the last house and going back? So that would be 1 mile from the shop, then another mile until you get to the last mile. And that's a total of 50 miles. So from the shop, so the driver have traveled 50 miles in order for him to deliver all of the 50 packages to the 50 houses. However, we will only not stop calculating based on that, since the driver has to return from the last house to going back to the shop. And that would be 100 miles. Therefore, if we say that if this is an algorithm, that means that it take 100, say, milliseconds or microseconds. It depends on the computer on what is the number of operations can be performed per second. So for example, if your computer has a speed of 1 gigahertz per second, that means that that's 1 billion operations per second. Okay, again, if your computer has 1 gigahertz, a speed of 1 gigahertz, the frequency, so that means 1 billion operations per second. So it depends. So let's just say that it's 100, say, nanoseconds. Okay, so one nanosecond per operation. So meaning for this algorithm, it took 100 nanoseconds to perform the algorithm. Now that's one implementation. However, we know that again, each of us been would have different solutions to the problem. So we will have different algorithm. Now another driver has a similar route, okay, delivering the 50 packages among 50 houses. And the driver looks at the route and delivers the packages from one house, going back to the shop, to the next house, and going back to the shop. So probably he just can't get all of the packages one at a time. So the driver will have to go back to the shop, then back to go to another house, and back to the shop, and so on and so forth until he would arrive to the last house, then go back to the shop. So what do you think is the distance that the driver traveled in delivering all of the packages? So here, if we will calculate from here, that's 1 mile, right? And go back, that's another mile. So meaning that's 2 miles. Here we have 2 miles from the shop, then another 2 miles. So which means the total distance traveled by the driver will be 1, 2, 3, 4, 5 until 50, and we just have to multiply it by 2, a total of 2,550 miles. Now, if you compare it to the previous one, it only took 100 miles for the driver to deliver all of the packages. So if let's just say that the first algorithm is the implementation of the one programmer, and this one is the implementation of the second programmer. So when we evaluated, the second programmer has more time complexity compared to the first programmer, or the first algorithm. Now, the second algorithm has more larger time complexity to compared to the second algorithm. Then we can present even equation. So again, this would be written in a function. So that would be f of n. Okay. So that's how we check. And that's equal to 2 times n. No, let's just say that the number of house would increase. We don't know much. But using the first algorithm, that would be 2 times n. And the second algorithm, that would be adding them all and simplifying. That's actually equal to n squared plus n. So our f of n here is equal to n squared plus n. Commonly, this is called the growth rate of an algorithm. But later on, we will be discussing how to evaluate more on algorithm using the different notations. Here is a comparison of different growth rates. Okay, you have here, let's just say n is equal to 1. Now, if our growth rate is 2n, which is just like the first algorithm presented, so these are the values, then n squared plus n. If we compare, now when we increase the number of n to 10,000, and the growth would be 20,000, while using the second algorithm, that would be 100 million. So here we can say that this one has a better algorithm compared to this one in terms of its time complexity. So the values again are called the growth rates of the function. Remember that one, growth rates. That's all for um, the comparison. Now we discussed how to, or we had already discussed two methods in determining the complexity or the efficiency of algorithms. One is using experimental and the other one is through growth rates. Now we will now discuss what is really a growth rate. When we analyze an algorithm, again, we usually count the number of operations performed by that algorithm. As I have mentioned earlier, and or in the previous discussion, previous slides, then we focus on the number of operations and not on the actual computer time. So in the second, if you compare the experimental analysis and the other one, which I call the higher level analysis, the experimental analysis focuses on time of execution, while the other one focuses on the execution based on the input. Now, that's actually um, based on the number of operations. Okay, we will focus on the number of operations. That n squared plus n is actually the number of operations in that algorithm. It's not that a correction would be, it's not the time that it would take, no, but the number of operations. We know that um, though we it's actually related, no, the number of operations can be related to the time complexity, but the time is much affected by the computer, okay, the speed of the computer. However, the number of operations is independent to the computer. We will be only be dealing or analyzing exactly the only analyzing only the algorithm itself without considering the speed of our computers. So this is because a particular algorithm can be implemented on a variety of computers, and the speed of the computer, as I have mentioned, can affect the execution time. However, the number of operations performed by the algorithm would be the same on each computer. So based on the algorithm. Let's have these examples. So this is written in C++. We have here C out, enter two numbers. C out is equivalent to print F or print or print line in Java. Then Cn is scan. Okay, getting an input. Here we have one operation. So this is one operation here. Okay, since we are printing enter two numbers. Then the second line has actually two operations. C in, meaning this line here is getting an input and storing it in a num1 and num2 variables. So this line actually has two operations. Now we have here an if and else statements. Okay, we have here one, so line 3. So we have here comparing no, two values. So that's one operation. Okay, line 4 has also one operation. Then we have here another operation. And the last line, how many operations do we have here? We actually have, first is printing, the maximum number is this one. The second one is adding max here to the printed one. And the last is end line, meaning that would be the end of this line. So all in all, there are 3 operations in the last line. So if we will sum all of them, we have 1 plus 2 is 3, 4, 5. Now, here, if we see here, if we analyze this one, this is an if else statement, which means either of these two would be performed. Now, since the first one has two operations, this one is only one, line 6 is only one, so we will be um, using this value. That's 2. So we add them. So 1 plus 2 plus 2, that is 5, plus 3 is 8. So therefore, the number of operations now for this algorithm is exactly 8. It's constant. Okay, that's for constant or fixed. Now, the number of operations performed in this algorithm is constant, and that's equal to 8. Now let's have a different, so a much longer, larger algorithm. So we have here C out. So again, that's one operation. However, we have another one here, which is end line, and that is 2 operations. Then we have count. This is 1 operation. So again, this is 2, 1, 1, and C in is 1. And getting an input. Let's proceed here. We have while num is not equal to -1. Do we know the value of num? I think we do not know. No, that's based on before that, let's analyze first this one. This is 1 operation. This is 2 operations. So you have adding, then storing it here. Then increment is 1. Getting an input is another 1. So we have here 5 operations. And again, however, as I have told earlier, we don't know the value of num, which is dependent on the input of the user. So we will denote it as a variable. So we will use a variable n. You can use x for analysis, but since we are dealing with the number of operations, we'll just have to use the variable n. Then we have here output, that's 1. Then putting sum here and end line. So total of 3. Again, this is 5n. Now these lines here, and you have 1. Then divide and average, that's 2. And we have 1. This 1. We have 3. This is 3. Now take note, we have to consider the larger one, the larger value for an if and else statement. So this is equal to 3. Sum them up. Of course, we cannot add 5 in since there's a variable. So we will add only these constant values as 2, 1, 1, 1, 5, plus 3 is 8, plus 3, that's 11, plus 3, that's 14. Then we add 5n, or just 5n plus 14. Therefore, the growth function of this algorithm, f of n, will be equal to 5n plus 14. So the number of operations here is 5n plus 14. This is not fixed. This is not constant since we have here n. Now we don't know the value of n here. So that's n. So if n is equal to 100, so that will be 100 times 5, which is 500 plus 14. So that's 514. If n is just equal to 2, so that's 24. So it's dependent on n. Growth rates of functions. Suppose that in a growth rate of functions, we suppose that an algorithm performs f of n, as if I have stated earlier, f of n basic operations to accomplish a task where n is the size of the problem. And suppose that you want to determine whether an item is in a list. So moreover, suppose that the size of the list is n. So to determine whether the item is in the list, there are various of algorithms. So we have to check the algorithm, and the basic method is to compare the item with the items in the list. Probably we'll have to use a search algorithm for this one, and wherever we can see the item that we are looking for, so that would be the output. However, again, if you recall the different scenarios, we have the best case, average case, and the worst case. Now, the best case would be the item that we are looking for is in the first value or element of the list. However, a worst case occurs when the one that we are looking for, the item that we are looking for, is at the last element of the list, or we could not find it at all. The average case would be it's in between the first values and the last values of the list. So the performance of the algorithm will depend on the number of comparisons performed. So thus, in the case of a search, so I have told you earlier, n is the size of the list and f of n becomes the count function. That is, f of n gives us the number of comparisons or operations done by the search algorithm. Suppose that on a particular computer, it takes c units of computer time to execute one operation. Thus, the computer time would take to execute f of n operations is c of f of n. Okay, again, suppose that on a particular computer, it would take c units of time. So a constant value. No? If we know how the function of n grows as the size of the problem grows, then we can determine the efficiency of the algorithm. So here is a sample growth rates of the different functions. Okay, if it's constant, the growth rate is just 1. If it's logarithm, so as you can see here, it's just a straight line. Now algorithm is almost a straight line, but it's actually the real graph of logarithm rather is just like this until it looks like a straight or a horizontal line. And we have here a linear function, then n times log n. So linear times logarithm. So n log n function. So these are the graph. So this one is quadratic. This is your n log n. Then this is exponential. No, this is exponential by the way. And this is your cubic. Cubic meaning to the power of 3. So exponential is okay, the n is in the exponent. So you can see here, if we analyze this one, so the largest growth rate function or the function that has the largest growth rate is the exponential, and the lowest is the logarithm. Of course, constant, so we will not deal with it since it's already constant value. If you check our previous um, example, the first algorithm in C++, written in C++, that's a constant. So wherever computer we place that algorithm, so the number of operations will be the same, and the number of time will be just minimal. Okay. So all in all, if we remove the constant among the choices, so the best choice would be the logarithmic function. So again, here's a comparison when they have tested it. So suppose that no, the speed of your CPU or the computer is 1 gigahertz. So again, 1 gigahertz means 1 billion operations per second. So if n is 10, so when you have an n growth rate, that's 0.01 microsecond. And you take note here, if you compare the growth rates, if that's an exponential function, if you just if you only even if you only have 100 n's, okay, iterations, so that would take 4 times 10 to the power of 13 years. A very, very um, large value. Okay, this is again um, getting now the time complexity. Now, based on that is if we have the speed of a computer. Okay, so this is just to display or to show you the effects of having such function, no, such growth rates of function. So again, if you have a function whose growth rate is an exponential, so it's not an idea. So better you have to change it. So you have to chop it down to smaller function or algorithms which has lesser growth rates. Okay, again, the best one will be logarithmic. Now, if you take a look at these, there are certain values wherein some of these functions are better compared to, say, linear. So if you will base it on linear, at some point here, now some point of n, some values of n, however, it's very much small values of n, um, n log n is better than linear. Exponential is also better than linear. However, if we increase the size of the number of n's, then they become worse compared to linear. So if this is the time, the number of size, and this is the time, or the number of operations, f of n, this will be the graphs. Okay. And by the way, our log is actually in base 2. So please do not be confused. Our log here is in base, expressed in base 2. Same with the next examples. Now we will be using 2 as the base of our logarithm. Okay, so we are now done discussing with growth rates. We proceed to the worst case scenario. Okay, this is just a tip, no, a tip. Why do we have to focus on the worst case of algorithm? So here's a sample graph. Now suppose we have here an input stands for an algorithm. No, this is an one algorithm, and this is the time that it would take, for a certain number of inputs. Now you have here now the graphs. So if the vertical, or if our y-axis is the time, so meaning the lower, the smaller the graph, the bar, and that would be the faster. So here, the smallest value would be our best case, while the largest would be our worst case. So we'll focus. So we'll in algorithm analysis. So we will focus on the worst case scenario so that we can have, or we can implement a better algorithm, so that again we can get, ideally we can get the log n um, growth rate function. Now here, the worst case and the best case are easy to calculate. However, it will be difficult to um, calculate the average time. Yeah, you'll have to get all of these values and get the average. So meaning there are a lot of calculations to be made. Sorry, there are a lot of calculations to be made when you want to get the average time. Okay, so that is why we'll have to focus here on the worst case. And why do we focus on the worst case, not on the best case? Of course, the best case is the optimal situation, or the optimal condition of the algorithm. So sometimes we don't want to deal with the optimal value, since that would be the ideal, that the fastest time, or the smallest, the fastest time that it would take for the algorithm to perform, so that would be best. But in reality, no, we have to deal with the worst time. No, we have to create a solution so that um, we can the worst time. Note that if a worst case worst case for the core, of course your program might, your computer might become slower. No, if the number of operations is too much and the growth rate is very large, what will happen to our computers? It might stop performing other operations. Okay, the worst case analysis would be much easier than average case analysis, as it requires only the ability to identify the worst case scenario, or the worst case input, which is often very simple. And this approach typically leads to better algorithms, making the standard of success for an algorithm to perform well in the worst case necessarily requires that it will do well on every input. That is why the author of this book or reference, suggested that we have to focus on the worst case. Then designing for the worst case would lead us to stronger algorithmic muscles, much like a track star who always practices by running up an incline. No? So if you, for example, if you test your algorithm in a very harsh environment or situation and it performs better in that situation, then how much more on a very good environment? So it would perform much faster, right? So that is why we'll have to develop or to focus more on the worst case. Okay, so that's just a tip from the author. Okay, a tip from our author, and it's taken from the book of okay the book that's from the book of Goodrich, Tamassia, and Goldwasser. That's Data Structures and Algorithms in Java, which is now sixth edition. So my reference is um, in the sixth edition. Now let's go to the last portions or sections of our discussion. Okay, algorithm analysis. So that's using asymptotic analysis. Now, how do we determine the growth rate of a function, di ba? And again, based on the tip, we'll have to focus on the growth rate. Okay, the worst case. And the solution for that one is actually big O notation. But before that, we'll have to discuss what is asymptotic, no, asymptotic analysis. When we analyze algorithms using the mathematical notations for the functions that disregards constant factors, we'll actually be disregarding later on the constant factors there, but not actually totally disregarding, but in getting the notations, no, we'll just have to disregard the functions, but there are other values there that will still need the constants. Anyways, that would be discussed later on. But let's have this first. Let's define first asymptotic. So again, when we say asymptotic, we will study the function of n as it becomes larger and larger without bound. So thus we can perform analysis of an algorithm by estimating the number of primitive operations executed up to the constant factor rather than getting bogged down in language-specific or hardware-specific analysis of the exact number of operations that executes in the computer, on the computer. So here, the asymptotic analysis would be dealing with n, no, as n becomes larger and larger, meaning as n increase infinitely. Okay. And not to the extent of infinite, but almost there. Okay, as the value of n grows larger. So that's asymptotic analysis. There are three notations again, and I have mentioned already to you big O notation, which will then be focused on getting the or describing the worst case, okay, the worst case scenario of an algorithm. However, we also have other notations, big omega notations and theta, notation. So big O, big omega, and big theta notations. There are other notations, little o, little omega, and little theta, but we will not be discussing it there. So if you are interested, you can. There are a lot of sources or references that you can look into. Okay, let's start with the big O notation. So we have here a definition. So let's um, let f of n be a function of n, and let g of n be another function. So mapping positive integers to uh, positive real integers. So that will be dealing only on positive integers or positive integers and real numbers. Okay, mapping positive integers to real or against real numbers. Of course, these are also real numbers. We say that f of n is big O, or read as O. O, a big O of g of n. So again, f of n is the different function, g of n is another function, but we can say f of n is a big O of g of n if there is a real constant. Okay, we can also write this one. The f of n is equal to O g of n if there exists or if there is a real constant, which is we denote c, and an integer which is greater than 1, such that f of n is less than or equal to Cg of n. For all n greater than our n sub 0. We call it as the initial value or the reference value. So this definition is again referred as the big O notation. Okay, here we read this as f of n is big O of g of n, and we write it in this form. All right. Now, this big O, as a sort of history, this big O notation is also called Landau's. I don't know how it's pronounced, but it's written in Landau. So this is called Landau symbol. So this one, it's called Landau symbol, which is a symbolism used in complexity theory, computer science, wherein we will be describing the asymptotic behavior of functions. Again, when we recall asymptotic, as we defined earlier, so it it has something to do with n as n grows larger and larger. Okay, we use big O notation for upper bounds, asymptotic upper bounds, meaning that's on the worst case scenario of the growth of the function. Now, if you will take a look at this graph, this is our given function. When we analyze algorithm, when we analyze algorithm, we express them in a function. Say, for example, if of n is equal to n. Now, g of n will be a different function, but will have much higher value of f of n. So that could be c times n, no, a constant times n. Then this is just an example. Now there is a certain value, we call it n sub o. So that's the initial value of n, wherein Cg of n becomes larger compared to f of n. So that means the worst case scenario is actually focusing from n sub 0, rather, n sub 0 rightwards. Now, as Cg of n becomes larger compared to f of n. So meaning ideally our f of n is running here, this is how our f of n functions, then the worst case would be this one here. If we recall our example, like in a linear search, this might be the worst case, wherein the item that we are looking for is at the last value or nothing, not at all. We have not found the the item that we are looking for, so which means we have a lot of iterations made, so only to get an answer. So that's the worst case. So other notations for big O, or other forms, or how do we read it, or how do we represent big O, would be these. We have f of n is order of g of n, or f of n is an order of g of n, a big O of n. So again, we can also write f of n is equal to O g of n, wherein we'll have a constant value later multiplied to g of n. Let's have this example. So if we let f of n be equal to a, so this is now our growth rate, where a is a non-negative real number and n is equal or greater than or equal to 0, then f is, and again f is a function, then we'll have here, okay, f of n is equal to a, and this a should be greater than or equal to a times 1 for all n is greater than or equal to a. Now, since our growth rate is a constant, then our g of n is equal to 1. Then our final answer will be the big O of f of n is 1. Okay, that's a special case wherein our growth rate is a constant, meaning wala siya yung worst case is just constant, we won't have a worst case and a best case and an average case. So the worst case, the best case, and the average case will be just equal since the growth rate is constant. Now, say if a here is equal to 2, then the growth rate of that function would be only be equal to 2, even if the number increases. If we will, if even if n approaches infinity, so the growth rate of the function will be just n. It will be just equal to 2 for all time. So that is why its big O notation is equal to 1. However, if for other cases wherein the growth rate is not constant, then we'll have a set of solutions. Say, for example, this one. So we already have an answer. Actually, this is our function. Now, f of n is equal to 8n plus 5. So the possible choices here would be finding, again, we have to find a C and then n sub O, or initial n. So we can just use C is equal to 9 and n is equal to 5. We'll just have to increase this one by 1, and this will be our n sub 0, meaning this function, our g of n, okay, our g of n, cg of n, will then be equal to 9n. So, but before that, our um, O of n, or our big O, is equal to, oh no, our O of g of n, sorry for that, our O of g of n will be equal to n. So this one will be just equal to n. So we'll have n. Now, why is it equal to n? Later we will have an explanation. Why is it that we only have our answer n? So now here we now have two functions. Now you have 8n plus 5 and 9n. So here we can say that this one should be bigger compared to 8n plus 5. We'll check that later on. Now we also have possible choices, and that's c is equal to 13 and n sub 0 is equal to 1. So that our g of n, our cg of n rather, will be equal to 13 n, which is much greater compared to 8n plus 5. Again, there are possible choices as long as that would be greater than this function here. You can have c which is equal to 10, okay, c which is equal to 11, and so on. But we will follow a certain algorithm on how to determine our c and n sub o. For this case, we will be focused on this one where n is equal to 1, or something value that our function will not be equal to 0. A certain value in our function will not be equal to 0. Now, for the rest of the slides, again, we will be using this, we will be calculating same with this one, the second option. But there are books, again, that have other ways of getting the g of n, or the big O. The big O will be just the same, but the cg of n would have different answers. But Tamassia's book, and his colleagues will be using this one here. Okay, okay, I'll just have to erase my writings so that we can see clearly what were in these graphs. Now I have here the graph. Okay, I have here the graph of the functions. Now GeoGebra is an online graphing calculator, so you can try it out. So at geogebra.org, just go to the calculator feature. Okay, this is our original. I use x since our x here, this is, take note that this is our n. This is our x-axis, so I'll just use x here, because if I will use n, I will have to define more lines. No? So instead, I'll just use the default variables in in this Cartesian plane, which are x and y. So you have x, just say this is 8n plus 5. Now this is the graph of um, 8n plus 5, which is colored in green. This is the graph, okay, that's in green. And again, the first choice, if you look at the first choice, that c is equal to 9 and n sub 0 is equal to 5. That's here. Now this is our CGX, okay, CG of x, 9x, or just say g of x, okay, that's 9x. Now, if you take a look at this, now this is our, again, original function, and this is our first choice for under big O notation. Here, before 9, before a certain value, that's 5 actually, this one. Now your n sub 0, here that's the intersection, the x value of the intersection of the two lines. Before 5, this one, this 9x is much greater, has much greater growth rate compared to our original equation, our f of n, which is 8x or 8n plus 5. However, as we increases the value, so which was not shown here, no, 9x has is performing. Sorry about that. It has much lesser, okay, compared to the other ones. Say for example, if you have two n's, the time is I think that's 18. However, for the original function, when n is equal to 2, that's actually 21. Okay, but when we increase, so we can say here that here our c at g of n has much lesser growth rate here in this portion compared to our original f of n. But as we increase the values, so as we increase, this line would actually will look like this, and our original equation will look like this. Okay, which means our g of n will now have greater values. So this is now where the worst case scenario occurs. Now when n is greater than 9. Now another possible solution is this. Okay, and that's n is equal to 8. G of n is 13x. So here we can say that at value 1, now at n is equal to 1, that will be the time that this function would have much greater growth rate compared to our original function, which is f of n. Now, as you can see here, if we now have 4n, our n is 4, now the time for our original function is just 36, 37. However, for the other one is it's more than, say for example, it might be 50 or more. Okay, that's the growth. As long as we can again get a function which has worst case compared to the original, so that would be a good solution. But again, we will have an algorithm or a set of rules to follow on how to get our C and N sub 0. Let's take this example of 5. Suppose our f of n, so again, this is our f of n, it's 5 into the fourth, 3n cubed, 2n squared, and 4n plus 1. Now do we get the big O, the g of n? Now in getting the big O, that's actually it's easy. We can just take a look at the given function and consider or get the function which has the largest growth rate, or simply the largest exponent if it's exponents, if they have exponents. Again, based on the graph, you recall the graph or the table, comparing the growth rates. So just get the term which has the largest growth rate, remove the constant, and that would be your big O. Okay, here, then our big O will be this one, n sub 4. Okay, but how do we get our C? Now, take note that we'll have to compare f of n. F of n should be big O of g of n. Okay, and that based on the definition, f of n should be less than or greater than c g of n. So we'll have to get c, and this g of n is our big O. Now, this is our big O actually, this one. So our problem here now is to get C of n. And how do we get that? Simply add all of the constant coefficients of the terms. So that's 5 plus 3 plus 2 plus 4 plus 1. And that will be our C, no, which is equal to 15. Okay, right? And again, our n sub 0 here is equal to 1. As long as the function will not be equal to 0, then we will consider or use n sub 0 is equal to 1. So therefore, the big O of our function is n to the fourth. Now let's graph it. So I graph it again using GeoGebra. So again, use this two. So this is our f of n, and this is our g of n. So here, if you take a look at this, so they intersect at 1. Okay, n is equal to 1. So that will be the case wherein they will have the same growth here. But if you check here in this portion here, and this one here, our original function f of n has greater growth rate compared to our g of n. But actually, as it goes larger and larger, the number of n grows larger and larger. Our f of n, when compared to our g of n, is much lesser. No, meaning our g of n now it has much larger growth rate compared to our f of n. And this is now where the worst case scenario begins. So I'm just showing you the graph so that you will understand that if this is our growth rate, if this is our algorithm, no, this is how our algorithm performs, then the worst case would be this one. Okay, this that graph. So another example. Now you have now different um, terms here, n log n and n cube. If you check which has the largest growth rate, I'll check our previous table. N cube has actually larger growth rate compared to n log n. So our big O will be n cube. Oh, that will be our g of n, and our c will be the sum of the constant coefficients of all the terms. So that's equal to 3. So this will be our c g of n, where our g of n is this one, n cube. So our c is 35, n. Now, know that n sub 0 is equal to 1. No, we have n should be greater than or equal to n sub 0. So which means n should be greater than 1. So this is how we write our final answer. F of n is a big O of n cubed, where c is equal to 35 when n is equal to 1. Which means our cg of n, compared to f of n, will be 35 n cubed. If you graph this one, this should be larger compared to 20n cubed plus 10n log n plus 5. Next, this one. So since there are only two terms, so log n should have greater function growth rate. So that's 5. Then our final answer will be this one. So here's a graph. So this is how a logarithm looks like. So this is our f of n. Okay. And this is our g of n. So that's this is cg of n rather, and this is 5 log. Remember that we will be using log base 2 of n. Our original function is 3 log n, 3 log base 2 of n plus 2. Okay, how about if we encounter this type of situation wherein there's only one term and it's an exponential, so you have 2n plus 2, 2 to the power of n plus 2. So we'll just have to separate this one, this constant exponent, so that the remaining would be the variable. So that will become 4 times 2 to the n. This will be our C. This will be our g of n. Since it has only one value, because it has only one term, so this means this is 0. The other terms are 0. So that means our C is just equal to the constant coefficient of our own one and only term. Then our C is 4 and sub 0 is equal to 1. And our big O notation is 2 to the n. Okay. Another case is that we cannot get an n sub 0 which is equal to 1, because when n is equal to 1, no, okay, I think, okay, so here, I um I think this should be greater than 1, because when n is equal to 1, you take a look at this, f of n, our f of n becomes 0. If you take a look at this function, okay, 2 plus 100 log base 2n becomes 0. So this should be just a correction, that should be greater than 1. So it could be n is greater than or equal to 2. Remember that our we will be using integers in our x-axis, and the y-axis would be the real numbers. I mean, it can be point something, but for the n, no, the number of inputs are integers. Now, we can't have an input or number of iterations, for example, which is half. Okay, so we'll use this one, an integer. So since it's greater than 1, n should be greater than 1. That means that starts with 2. So n, the final answer here would be n, okay, is greater than or equal to 2. All right. Now, going back to our previous example in the first algorithm, so what do you think is the big O of our function? So since this has 8 operations, no, you have 1, 2, this is 1, 1, 1, this is 3. So we'll be considering these two. You have 1 plus 2 plus 2 plus 3, we'll get an 8. So a total of 8. So therefore, our f of n is equal to 8. And the big O of a constant growth rate is equal to 1. Okay. Then this one, so if we recall, this function is n squared plus n, I think. No, if we recall, is it n squared plus? No, I think it's not n squared plus. Let's just count it again. Okay, just have to count it again. We have here two operations. 1, 1, 1, 1, 2, 1, 1. But there are n, we don't know n, so that would be 5n. And here we have 3, 1, 1, then 1. So we'll use this 2. Then we have 3 here. So sum them up. This is 5, 6, 7, 10, 13. Let's check. 5, 8, 1, 2. Okay. Is it 13? Let's check. I forgot what's the answer to this one. So we have line 1 to 3 has 5 operations. Line 1 to, okay. This with negative 1, 1 to 4. Ah, yeah. This is 5 operations. Then lines 10 to 13 of 1, 3, 7. Ah, okay, I'm sorry. This is 2. So this is 3. Ah, yeah, that's correct. That's 14. So we'll have 5n plus 14. Okay, this is now our 5n plus 14. So which means 5n plus, in order for us to get our c, that should be 5 plus 14n. And that's 19n. So our cg of n is equal to 19n. Therefore, our big O, no, the big O of our function is the big O of our g of n, which is equal to n, right? So that's n. So that's how we analyze or get the big O notation of our function. So you have f of n is, this will be our final answer. The big O of f of n is n. Okay, more examples. Now let's analyze this one. How do we analyze this? Let's start with n is equal to x. Okay, for this method. So that would be 1. So, so that would be 1. Then the double, since this is creating an array based on n, so the array will be created based on the n inputted. So we might say that's n. Declaring an array. If it's only a variable just like this, so that would be a 1 operation. Then we'll have here 1, 2, 3. 3 inside this loop. Okay. Then another loop here. 1 operation. Another loop here. And 2 operations. And 3 operations, I think. However, here it would depend on j. And here it would depend on n. So which means, what would happen here? Which means, let's just say that n or j are just the same. So that would mean that it would be n squared, right? So you just had to add these. So 3, 3, 1, 3, 1, 3, 2, 3 should have 12, I think. 12 n squared. And for the termination, I think you'll have to add that. We will have, since it's termination here, then return has 1, right? So if you will add all of these, so you will get 3. I will start with with just the largest order. That's n squared plus n plus 3. I think this would be the answer of, or the f of n. Okay, and therefore the big O is n squared. Our c will be 12 plus 1 plus 3, that's 16, right? So that is how we get the big O notation. And how about this one? So we'll just have 1 in 1. So here is 3. We'll have 2. This is 3. And 1 for termination. But inside the loop, it's based on in, right? And another one. So we'll have 1, 2, 3, 4. 4. Then we have, this is 7, 8, n. However, we also have n here, so that will be 9n, which means our big O is n. And our C is 13 when n is equal to greater than or equal to 1. Here is a summary of descriptions of the growth rates of the function. For constant, it does not depend on n since it's constant. For logarithm, it grows slowly, probably at the very first values, it grows abruptly, but as the number of n grows larger and larger, the growth rate becomes very slow. Well, n is dependent or proportional to the size. Now the growth rate is proportional to the size. For n log n, so that's faster than linear. N squared, in quadratic, is much faster than the previous ones, and the exponential is so much faster than the others. That's the comparison of the growth rates of the big O functions of the different um, growth rate functions. Okay, last we have asymptotic analysis. Comparing asymptotic again, big O deals with the worst case, while big omega rather deals with the best case scenario. So still have to get the big omega. So I'm just presenting it here so that we'll have an idea how to get the big omega now when we consider the best case of the situation. So it's less than or equal to another function. Okay, just as the big O notation provides an asymptotic way of saying that the function is less than or equal to another function, the following notations provide notations, asymptotic way of saying that the function grows at a rate that is greater than or equal to that of another function. That's for big O. So big omega is for less than or equal to another function. Okay, take note of this symbol, omega. Okay, in short, if this is our function, so the big omega is here. That's the best case. Example, this one, we have 3 log n minus 2. Now, which among these two has the lowest growth rate? So I think that's, we'll just have to check first, no, by the way, so that we can get the term, no, the, according, based on the book, we have to simplify it further so that we can get the smallest one. So that would be this one, and we'll have to. So we will realize later on that this actually is much larger compared to this one, which means our best case would be n log n. So that would be our big omega. Then to get the C, that's equal to 1, and n is greater than or equal to 2, because here in log n, no, um, okay, I forgot to create the graph, to include the graph. But again, if you recall, log base 2 of n, when n is equal to 1, it becomes, or it would be equal to 0. And therefore, f of n is in omega of n log n for n is greater than 0. So that's just big omega. Okay. Next is Big-Theta. So please change this. This is not omega, but theta. Okay. We write f of n is equal to Big-Theta of g of n if there are positive constants n 0, c sub 1, and c sub 2 such that to the right of n sub 0, the fn always lies between. No, our fn is between c sub 1 g of n and c sub 2 g of n. So again, if you recall the comparison earlier, so our our Big-Theta should be in between the worst case and the best case. So here are some examples no, in written in layman's term. Okay, if as a summary, okay, if this is the case, the delivery will be there within your lifetime. So that's actually lifetime. So that's a worst case. So we'll use big O notation. I can pay you at least $1. So at least is the best case. So that would be big omega. So that's big omega. So you write this big O. Then the high today will be 25 degrees. So it's in between 19 degrees and 25. So that's Big-Theta. So again, capital letters. And this one, exactly 1 kilometer. So our O, omega, and theta are just equal. So Big-Theta is just exact. Okay, this is how we compare those three notations. Also, when based on definitions, we have this. So big O is just like uh, the function is less than or greater than g of n. Big omega is like the function is greater than or equal to um, big omega of g of n, while theta is equal. Okay, the function has lesser grade throat compared to our the big O. Okay, while in big omega it's the opposite, and so on. So we have these um, comparisons among the three. Okay, big O deals with the worst case, big omega the best case, and big theta theta is deals with the uppercase, and these are the mathematical expressions um, of the three. Okay, the three notations. And we are done with this lecture. Thank you, and see you on the next discussion.